Here's problem 12.3. The meter stick is supported by a knife edge at the 50 centimeter mark. Doug hangs masses of 0.4 and 0.6 kilograms from the 20 centimeter and 80 centimeter marks respectively. Where should Doug hang a third mass of 0.3 kilograms to keep the stick balanced? All right, let's see what we have here. We have a meter stick, and it's balanced at its center at a point of 0.5. And we have a mass, M1, equal to 0.4 kilograms, located at x equal 0.2. And we have another mass, let's say at M2, equal to 0.6 kilograms, located at x equal to 0.8. So if we were to start making a free body diagram of this, we would have a M1G pulling down over here, and M2G pulling down over here. Of course, there would be weight to the meter stick, and there would be a normal force at the pivot here. Also, since it's pivoted on the center, I know that mass 2 is greater than mass 1, so this thing will probably rotate clockwise to the right unless I put the third mass on the left-hand side. So that's what I'm going to do. I'm going to place my third mass somewhere here on the left-hand side, such I'll have a M3G coming down like this, and hence it'll be located at a position equal to X on the meter stick. All right, so that'll be my location there. So that looks like my free body diagram. I have a problem with trying to do force equilibrium here. Everything's in the y direction, but I don't know what the normal force is, and I don't know what the weight of the meter stick is. We weren't told that. So it looks like I really need to focus in on doing a torque equilibrium and choose my position as being the pivot point so I can eliminate those unknowns from my consideration. So that's what I'm going to do. I'm going to choose this actual pivot point here. Let's use orange here as being my point. I'm going to call it A. So if we calculate the torques about A, we should get 0. The summation of all the torques about point A should be 0. Now I'm going to have these forces, and I have these respective moment arms. For mass 1, the moment arm is 0.3 meters, because that is the distance to the line of action of that force to the pivot. And for mass 2, it also is going to be 0.3 meters, because that's the distance from the line of action of that force to the pivot as well. The weight and the normal force have 0 moment arms, so they are not contributing to the torque. And then I have, let me do this. I have the line of action of this mass 3, and its distance is this distance d here, which is actually going to be equal to 0.5 minus x, where x is the location of that mass on the meter stick. So the distance d is 0.5 minus x, and we'll keep that in mind. So now I can set up my torques. Now as far as the counterclockwise rotations, mass 1 and mass 3 are going to try to make this thing rotate counterclockwise, which would be positive torques. And mass 2 will try to make this rotate the opposite direction, clockwise, which would be a negative torque. So I'm going to have moment arm 0.3 times force mass 1g, that's a positive torque, plus moment arm 0.5 minus x times force mass 3g minus the third torque, which is 0.3 meters times force mass 2g. And all this should add up to 0. Now, I got g in every term, and so if I divide both sides of the equals by g, I can get rid of these g's. G. So now I have 0 is equal to 0.3 times mass 1, which is 0.4, plus 0.5 minus x times mass 2, which is 0.3, and minus 0.3 times mass 2, which was 0.6. So we have 0 is equal to 0.12 plus 0.15 minus 0.3x minus 0.18. So I have 0.3x is equal to 0.27 minus 0.18, or 0.09, or x is equal to 0.09 divided by 0.3, which is actually going to be equal to 0.3. So on the meter stick, the location of the third mass is at 0.3 meters, or 30 centimeters. That's the position where I should put the third mass of 0.3 kilograms.